Recording has started. Okay. Okay. So in today's class, we focus on this. Focus on two applications of the divide and conquer algorithm. I think actually we have already seen use of these divide and conquer algorithms in the sorting problems. Now, today's problem, the first problem that we do today is integer multiplication. So I think all of us are familiar with this problem, integer multiplication. So what is this problem? It's the first problem that, sorry. The first problem is integer multiplication. Okay. So what is the integer multiplication problem? It's like given two integers, two or more. So let's focus on two. So the problem is that input is two n-digit integers x and y. Okay, two n-digit integers x and y. So what do we want? We want to know the value of xy. So okay. So it's a very easy problem that we already know. We have covered in our, I think in basic school, so we have seen this problem and we can easily solve it, right? So now think about like how many operations you have to do, because there are these are n-digit numbers. So like when you multiply some, let's say 2, 3, or 4-digit numbers, what is the or how many number of operations you do? And by operations, we mean the basic operations of addition and multiplication that we do while finding the uh, multiplication of the two numbers, right? See, why we are interested in the basic operations? Because we wanted in every in this uh, algorithmic study, we focus on the complexity, the time complexity of that problem. And if you recall, that time complexity is basically depending on how many primitive operations you are doing, right? So counting the number of primitive operations is very important in this case. So that's why we like previously when we compute to multiplication of two or three numbers, we just compute it. Now we also look it in the look it in a different angle. We look at how many operations we are doing while executing that multiplication. Okay, so let's say so let me define the primitive operations. So it's clear why I am focusing on the primitive operations, because our running time will be depending on those primitive operations. If you recall that your running time is when we are discussing, I think when you have learned the order notation, so it's basically the number of primitive operations that you perform. In an algorithm, the running time is the number of primitive operations that requires to perform that algorithm. Okay, so we need to count that one. So the primitive operations, what are these operations? One is addition that we do, addition of two single-digit numbers, and multiplication of two single-digit numbers. So these two are our the primitive operations that we do. So now let's say we want to multiply, let's say x equal to some 5, 7, 9 and y equal to some say 1, 1, what is it? 1, 3, 4. Okay, so you want to multiply, let's say we, okay, it would be better if I take 4 digits. Okay, the 0 here and 5 in here. Okay, so let's say we want to multiply these 4-digit numbers. So what is our school level algorithm? Like we write two numbers, one after another. Now we multiply, let's say the first number actually, we multiply, we take this number, the last one, the lowest decimal number, and we multiply it with all the numbers in the first one. So it's something like 2, 4, 5. That's it. 35, 4, 9, and 25, and 3. I think 28. Is it correct? Did I compute correctly? 5, 4, 5, 9, 3, 28. I think I computed correctly. Yeah. So then what we do, we leave a space. We leave this space. And we multiply 4, the next number, with all the numbers in the above, right? So if we do that, 6, 3, 28, 1, 23. This would be the number, right? The total you are talking about. Okay, fine, maybe. No, it's important to like think about the steps. So that's why I'm explaining it. Otherwise, there is no need to explain. I know it's the total, finding the total one is not the target actually. The steps are important. What we are doing at each step, we need to focus on that. I have, okay, is that? Yeah, so primitive operations are basically the addition and basic addition and multiplication that I think already have defined, that it's a basic addition of two numbers, two single digit numbers, and multiplication of two single digit numbers in this case. So someone is raising hand. Okay, next is, yeah, next is fine. I just, someone is raising hand. Yeah, okay. So next number is 0, 7, 2, 3, 7. Where was I? 0, 7. Yeah, and the last one would be the same number. Okay. So this is what we have done in our school days, right? This is the algorithm. So what is at each step what we are doing? We are taking a digit and we multiply it with every single digit of the other number, right? So this is the basic algorithm that we have done in our school days, during our school days. Okay, so whatever summation will come, that will come. I am not interested in the result. You can find it easily in the calculator. The important is the process. So when we are the way we are solving it, what we are doing at each step of this algorithm, these are the steps that we perform. Okay, and after that we sum all these things. So at each step, what we are doing, we are multiplying one digit to all the digits of the other number. So this digit to all the digits of this number, x in here, right? Okay. So this means that at each time, so if you think about this 4-digit number, so how many multiplications we do corresponding to 5? We do 4 multiplications, right? And in each step, we do this 4 number of multiplications. And how much and how many of these 4 multiplications we do? We there are 4 numbers in the second digit, so there are 4 digits in the second number. So that means we perform this multiplications 4 times, right? Yes, equals to number of digits. Yes. So what we are doing is that total number of operations, if we want to count that how many primitive operations we did in this whole process, that is basically 16 multiplications, right? 16 primitive operations. And some like more, like almost 16. There may be some a little bit more operations that you need, like you have to add those numbers. So you can say the operations would be like a little bit more than 16, but it's 16 primitive operations, you can say. So basically, if you think about in terms of n-digit numbers, so you need that order n square many multiplications, right? Many operations. Okay. So if you think about instead of these 4-digit numbers, you have n-digit numbers. So how many steps you have to perform? N number of steps at each time. N number of primitive operations at each time, and there are n digits. So there are n square number of primitive operations in there. Okay. So why it's order? Why it's not actually 16? What I'm saying is that it should be a little bit more than 16. And in order notation, I am just writing order n square, just to clear that doubt. Because in 16, you can see that there would be some additions we do in each step. We will do these additions also. So there are something like 1, 2, 3, 4, 3, 4, 5, 6, 7. So there are some 8 type number of additions. Okay, so that's basically some order n addition. So in this operation, it's order n square plus order n additions. So total number of operations are like this. But since you know that in order notation, order n square is a dominating part, so we can think of this as an order n square many operations. Okay, so the running time of our known algorithm of our school level algorithm is order n square. Okay, so is it clear? Like, can you observe the steps that we did? So It's a simple multiplication that you know in your school days, and 8 additions is basically this. You have those digits, right? Some you have this. You have to multiply. You have to add this number. Then you have to add this number. Then you have to add these numbers. Then you have to add these numbers. So if you count like how many additions you have to do, so there is addition of single digit numbers. They are all single digit numbers. So it's addition of these, somewhat like more or less 8. Oh, 7, 8, whatever. It's just a factor of n. That's what I'm saying. So if you look at like, if you think about n numbers, so this addition cannot be more than order n. Okay. That's the main factor. तो इसीलिए मैं यहाँ पे लिखा था कि ऑर्डर n स्क्वायर प्लस ऑर्डर n नंबर ऑफ प्रिमिटिव ऑपरेशंस. ओके, ऑर्डर n वो सेकेंड टाइम जो एडिशन करते हैं हम लोग, पहले फर्स्ट वी राइट दोस नंबर्स, फर्स्ट वी राइट दोस मल्टीप्लिकेशंस and then we add them, right? So the next step of addition that can be done in order n type. Okay, is it clear? So वो 7-8 is not that much problem. I just cleared that why I did not write 6. Why I'm saying that it's more than 16. Yes, carry addition will be counted. Yes, still it is in order n. Okay, so the main focus is that you are spending how many operations you are spending. You are doing order n square many primitive operations in this in this algorithm, right? Is it clear? So can you see that how many like what is the running time of your school level algorithm? Now I think you can analyze that it has running time of order n square. Okay, the known algorithm, the way we solve the multiplication of n digit numbers. Okay, fine. Any doubts or questions? Okay. Okay, fine. So if there is no question, then there is a very important question in there, that can we improve this? So the question is, can we do better? So this is yes. So since I have already told you that this class is about divide and conquer algorithm application, so we will see an application of this divide and conquer algorithm to this problem, to this integer multiplication problem. Although that will not improve the running time to like a significant amount. Yes, yes. That's what in terms. Can we do better means can we reduce the running time? That's the question actually. Always like in algorithmic theory, whenever someone is asking that can we do better, that means that can we reduce the running time complexity, or can we reduce the space complexity? Okay, so doing better in algorithm means always reducing the complexity, complexities actually. Okay, so the next step will is actually a very known algorithm. although it's a very clever use of this divide and conquer strategy. Although I'm saying that it improves the running time, but it's not a significant improvement. Like it's not a linear time algorithm. That's what I'm saying. That it's still open. That you can try to find an algorithm to solve this problem in linear time, integer multiplication. Okay, it's not achievable in linear time, but this algorithm is a little bit improvement of this one, that known algorithm. So divide and conquer strategy means what? We need to create some sub problems, right? We need to find a sub problem, find sub problems, that we can divide this problem into some smaller sub problems, and then we can divide and solve the smaller one, and then we can get the solution for the whole problem. So that's the divide and conquer strategy. So here what we do is that we divide these numbers, not divide in the sense of division of two numbers. Let's say okay. Okay, so let me write the name. So this algorithm is known as Karatsuba algorithm. So how does it work? It's like, suppose you have, so we have two numbers, right? In here, x equal to 5790 and y equal to 1345. Okay, Karatsuba B. That's okay. My handwriting is not that much good. Actually, very bad. So it's Karatsuba B. Karatsuba algorithm. Okay. So what we do is we think of these numbers, we divide them into half. Divide them into yes, Karatsuba. Divide them into half. So first two parts, for in here it's a 4-digit number. So for that we can take, we consider this as A, we consider this part as B. Similarly, we consider this part as C. Let's say we consider this part as D. Okay. Just considering them. So you can see that all these are n by 2 type numbers. If this x is a 4-digit number, A and B are the two-digit numbers. Similarly, y is a 4-digit number. C and D are two. It's a name. इसका नाम है करात्सुबा. ये प्रोबेबली जैसे नाम से लग रहा है कि जापानीज है, शायद, मुझे ओरिजिन नहीं पता, पर जिसने वो एल्गोरिथम डिजाइन किया था उसका नाम करात्सुबा है. तो आई थिंक इसी से इसका नाम हुआ है इस एल्गोरिथम का. बट दैट्स अ नेम. आई मोस्ट लाइकली कुड बी अ जापानीज नेम. गेस है मेरा, बट it's okay. Don't focus on the name, focus on the algorithm. Okay, so this A and B, if you can see that I have started with a 4-digit number. Now I'm trying to divide this, trying to reduce this number, represent this number actually using the 2-digit numbers, and then my idea is that use this recursive process on these small numbers, and then somehow if we can design a recursion, then we can find the solution. Okay. So now how to do it? Like, okay, let's say we assume this as this part as B, this part as C, this part as D. Now what? Now what are the steps we do? Okay, so next thing is that, so first step, what we do is compute AC. Okay, so we'll compute AC. We'll see when we compute. These numbers are not. Then we compute BD. Okay, so AC is what? A is 57, C is 13. If we multiply, then what we get? 1, 2, 5, 71, and 57. So it's 14741 if I'm not wrong. Okay. This one, then if we can compute BD, B equal to 90, D equal to 45. J is 045 and 036. So it's 05. Mm, 04 4050. Okay, step 3 is that we compute A plus B into C plus D. So A plus B means 5730, that is 10, 60, 70 into here C and D. If we, oh, sorry, AB is different, 90, sorry. It's 147 into, that's 58. 147 into 58. That is some number. I don't know. I don't want to compute. What is that? 8526. Okay. Okay, fine. So 8526. Okay, Anatoly Karatsua. Oh, you got the origin. Okay, then maybe Russian or Polish. Anyway, 8526. Okay, yeah, Russian. Okay. 8526, and then in the final step, what do we do? We do this. Whatever we are getting in here, this minus or ACBD, whatever order you can say. So 8526 minus 4050 minus 741. So can you see? I mean, if you compute this, I think it will be equal to some number 3757. Okay, 3735. Okay, so we have this number. Now what do you do is write in this way. Okay, so the first we computed AC and we have 4 numbers, so we add 4 zeros in here. Okay, then we computed what? 4050, right? BD. So directly we write, it's a 4-digit number, we write it in here, and last we computed this 3735. So sorry, should be one step lower. So 3, 3. Okay, so can you add these numbers? So if you add 0, 5, 5, so is it the same? No. That's 7787550. Yes, this is the number that we are getting. And what is the number we get when we multiply? It's the same number, right? That we get when we multiply those two numbers. So 7787550. Okay. So now you can see that we obtained the same result that we have obtained through our school level algorithm. So now the question is, what is this? Like how we can, like, how this works? First of all, how this works? Like, out of which you just divide the numbers into two parts and then you multiply them and then you get it. How does it work? It's for two numbers, it's directly coming into the answer for 4 digits. But if you have like even if you have 4 digits or more than that, actually, if you think about 9 digit, 10 digits, then if you divide, okay, one more thing, if the numbers are odd, so I have started with an even digit number because it's when we are dividing, it's a kind of n by 2 division. So uh, the n in here is 4 n digit numbers. If the n is odd, for example, if you consider a three digit number, then one part would be like 2 digit number, one part would be a single digit number. Or if you consider a 5 digit number, then one part would be 3, another would be 2. Okay. So it's not like every time it has to be equal part. Okay, it's depending on the value of n. But two numbers must have the same n digits. I mean, the two numbers should be of n digit numbers. Okay, it's not like one is n digit, another is smaller. All right. So I think the point is clear. So now the question is why and how. It's kind of very tricky to understand that how can anyone come up with this kind of idea, and what is actually happening in here. Okay, so yeah, if you take 11 digit numbers, then you will divide one part into 6, another into 5. So yes, that's what I'm saying. So see, if the digit is large, then your multiplication does not work directly, right? So why we are trying to divide it into small parts, into half? So we apply it recursively. So for example, when you have, let's say you saying 11 digit numbers, so suppose your number is of 11 digits, two numbers of 11 digits, then you divide one part into, this part is, let's say 6, this is 5, and this part is, let's say 6, and this is 5. And let me name them part 1, part 2, part 3, part 4. So this is our x, this is our y. So when we yes, divide into half, yes, or some, no, it's actually the algorithm is divided into half. I mean, otherwise the rule that we have just seen would not work, will not actually help you. So what we do is that this P1 is a 5-digit number. Let me explain. Let me explain that. P1, 5-digit number, right? P3 is also 5-digit number or 6-digit number. Okay. There is a P4, right? P4 is 5-digit number. P4 is 5-digit number. So we can multiply them. Okay. So once we multiply this P1 and P4, it's the same thing that we do. We apply the same algorithm. We again divide these numbers into two halves. We can divide this 5-digit number into two part, and this 5-digit number or 6-digit number, whatever, into three part. So no, it's not Vedic mathematics. It's kind divide and conquer algorithm. It's like you are dividing it into parts. What do we do in divide and conquer? We divide. We first we take a problem and we break it into smaller sub problem. So if you think about your 11-digit numbers is the original problem, that will break into two sub problems, P1 and P2, and X for Y it's P3 and P4. We divide it into smaller parts. Then we again apply that this division. We again divide these problems into smaller sub problems, and we try to solve till we reach the single digits, and we can multiply them. Okay, so that's the idea of this one. So we are recursively applying this method until we get a single digit, and then we finally come up with the answer. So what we do is that we start with n numbers and we break the numbers into its half, almost half that we have seen, that we have already seen in here. We break these numbers into halves, half of the size, n by 2 numbers, n by 2-digit numbers, and then we then if you see, then we are applying these steps, right? We have to apply these steps for that algorithm. So this step 1 is computing A and C. Now both A and C are in this case 2-digit numbers, but if you think about n-digit numbers, this would be n by 2-digit numbers, right? Similarly, we compute B and D. That's also an n-digit number. N by 2-digit numbers. I mean multiplication of n by 2-digit numbers. B and D both are n by 2-digit numbers. So this multiplication is also a multiplication of n by 2-digit numbers. So whenever I am multiplying these n numbers, I will look at these n by 2 divisions. Okay. And that's similarly, like I will keep on applying the same recursive algorithm on these parts also. Then we compute A plus B and C plus D. A plus B and C plus D both are n by 2-digit, n by 2-digit numbers, right? So all this computation in throughout all this part, we are looking at this n by 2-digit numbers, multiplication of n by 2-digit numbers. So from our problem of having two n-digit of multiplying two n-digit numbers, we actually looking at some problem where we are multiplying two n by 2-digit numbers. Okay, so this is what the divide and conquer algorithm do. We divide the problem into smaller sub problems. So these n by 2-digit numbers are the sub problems. Yeah, I'll come. I'll come. Yeah, that I'll come. That how we are writing these rules and all, how we are doing these computations. I'll come to that. But first, get this idea. Yes, there are reasons for that. But first think about this one, that how the recursive idea is working in here. So we started with n-digit numbers, then we break this n, then we actually our problem is to compute this multiplication of these two n-digit numbers. From there, we are focusing on when we observe these rules, when we observe this step 1, step 2, or step 3, rules, we are actually focusing on multiplication of two n by 2 digit numbers. Yes, n by 2 is n by 2 means you can take the floor or ceiling value. So for example, when n is odd, I've told you that you can divide it into 3 to the 5, 6, 5 if it is 11. So this is how you can think about the divisions. Okay. So okay. So when so at each step, each steps, the step 1, step 2 in here, if you look at, we are focusing on the multiplication of n by 2 digit numbers. Okay. Right. So basically we are looking at a sub problem of size n by 2. Okay. And then we keep on recursively doing this, because when we try to find the multiplication of AC, again we are asking the same question, that what is the multiplication of two n by 2 digit numbers. So for that we again have to compute some other AC. I mean, in that case, whatever the values of AC will come, we'll have to compute that. So basically that means that we are reducing our we are looking at smaller we are keep on recursively applying this same technique until we get the multiplication of AC to be two single digit numbers, and from there we can compute the whole solution, right? So do you get the recursive idea behind it, that how we are breaking the problem, that we have a main problem of multiplying n digit numbers to smaller problem having n by 2 digit numbers? Is it clear? Okay, so I will write a pseudocode for this one. So then maybe it will be a little bit clear. So if you look at the pseudocode, so if you say Karatsuba, let's say XY. If okay, so we apply this XY, and when we apply Karatsuba XY, we think of X as some you can say it's actually something like, you can write it as 10 to the power n by 2a plus b, and y as 10 to the power n by 2 c plus d. Can we write it? So is everyone agree with me about this? Okay. Uh, do you know the decimal representation of a number? Like, for example, this number, 57, whatever, 5790. Yeah. Or rather, I will take the non-zero one, 1345. Yes, I'm writing. So 1345, can you represent it into decimal number? So if you think about its representation, oh, it's actually this example is to show you that if you compute these numbers instead of doing the same procedure that we have done, we can arrive at the same result. But yes, in our case, like we have to, for recursion purposes, we have to break it till we have to like find the correct way was to think of this as a multiplication of 57 and 13 in scientific form. Scientific form Okay, I don't know what scientific form means, but there are like decimal representation of a number. So this 5 is unique. Then the 10th first place is 4. Yes, yes, yes. Oh no, 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 not that one. Okay. In fact, base 10. Yes, yes, yes. Of course, it's basically decimal numbers we are dealing with. So I am talking about the decimal representation of this. Uh, can we write it as 4 into 10 plus? Okay, let me just start it. Plus 10 into 4 plus 10 square into 3 plus 10 cube into 1. Can I represent this number in this way? Yes, that representation I was talking about. Okay, fine. Now, can you write this one as 10 square, 10 plus 3 plus 45? Okay, expanded form. Okay, we call it a decimal form anyway. Can we write this number in this form? Okay, so what is this? This is a 4-digit numbers. So it's 10 to the power 4 by 2. 10 plus 3 is 13 plus 45. So this is our C. If you look at this part is C, this part is D. So this is our C, this is our D. Okay. So how am I writing these two terms is clear now? Fine for everyone? Okay. So, okay. So we can write it in this way. Now what our algorithm is doing is that compute, this is not the part of the algorithm, compute AC, compute BD, compute A plus B, C plus D. That's the thing I think. Yeah. And then compute now when you compute AC, what do? You call Karatsuba AC. You call Karatsuba BD. So I'm recursively calling this function. Okay, it's fine. Now you understand why I'm saying that this is like Karatsuba A plus B C plus D. Okay. So we compute all these steps, and fourth is that rule that we have seen, BC plus D minus AC minus BD. We compute this, and that will give you and we add all this. Now about the addition part. Okay. When someone is questioning that why I put 4 zeros in here and why I am adding it in this way. So the answer lies in this division. Okay. Now let's say you have seen that I have written x equal to 10 to the power n by 2 a plus b and y equal to 10 to the power n by 2 c plus d, right? So if you compute xy, what will come? This, right? You can write x into y in this form. Now, this means 10 to the power n AC plus 10 to the power n by 2 AC plus BD. No, sorry. AD plus BC. Sorry. AD plus BC plus BD. Okay. Okay. So that's why now you understand why we are focusing on compute AC, BD. Okay. You can guess that in the solution, if I know AC, to put why I put 4 zeros, it's a 4-digit number. 10 to the power 4 is there. So AC is this value, 741. That's why I put 4 zeros behind it. Okay. So it's basically nothing but 741 into 10 to the power 4. Okay. And then we compute BD. BD is your decimal place or the leftover place after taking n by 2 terms out of it. That's why we just add it. Okay. It's a multiplication of two n by 2 digit numbers. So that means the multiplication would be some n digit number, which is in here. Now, also we have to add them. So now we so we have, so what are the things we have to find? We have to compute AC, BD, AD and BC, right? Okay. So if you compute this AD and BC, okay, so can you write a recursion relation corresponding to this problem? Like what should be the recursive relation corresponding to this problem? What if we just compute this thing? That we first compute AC, then compute BD, then compute AD, and then compute BC. And then we simply find this summation. We don't have to do all these steps of like steps 3 and 4 seems meaningless or unnecessary, because we can directly compute AC and BD, and then we can compute AD and BC, and then we can directly compute the multiplication of XY, right? Still recursive calls, but why we are doing this A plus B, C plus D? It's not needed, right? You can see that directly you can do AD and BC. Why does he do this kind of thing? So for that, think about the running time of this. Think about the recurrence relation corresponding to this problem. So what should be the recurrence relation? These are my sub problems. These are sub problems. Okay. So each sub problem is of size n by 2. Okay. So if you think about the recurrence relation, we have this corresponding to order n is for addition. Okay. So we have this recurrence relation. All of you agree with me? Is it okay? So what is the solution of this second relation? You have, I think, already you know how to solve these second relations. So what is the solution for this second relation? रिलेशन समझ नहीं आया। रिकन्सिलिएशन में आई मीन कहाँ पे डाउट है तुम्हारा? अच्छा ये हाँ ये रिकनेक्ट कैसे आया? ओके टीएन ये टीएन जो है वो तुम्हारा टोटल रनिंग टाइम है एन डिजिट नंबर्स को मल्टीप्लाई करने का। अब एन डिजिट नंबर्स को मल्टीप्लाई जब करने जा रहे हैं तब हमने क्या किया कि उसको इसमें वैल्यू रख कर, वैल्यू मीन्स वो जो सब्स्टिट्यूशन मेथड, देखो वैल्यू रख के सॉल्व करना बहुत डिफिकल्ट है एक्चुअली, वो ट्रायल एंड एरर मेथड है। द बेस्ट मेथड जो है वो है मास्टर मेथड। अच्छा हाँ ऑर्डर इन, हाँ मास्टर मेथड, यस यू कैन यूज मास्टर मेथड। हाँ ऑर्डर इन इज फॉर द एडिशंस दैट वी हैव टू डू except for the multiplication. Yes, order n square. Yes, master method. नो द ये रिकरेंस ऐसे आया कि हम n नंबर्स को मल्टीप्लाई, n डिजिट नंबर्स को मल्टीप्लाई कर रहे हैं। तो n डिजिट नंबर्स में अब हम देख रहे हैं कि n डिजिट नंबर्स को हम ये n बाई 2 डिजिट नंबर्स के मल्टीप्लिकेशन से सॉल्व कर सकते हैं। हाँ मास्टर मेथड इज द बेस्ट वे टू डील विद दिस प्रॉब्लम्स एक्चुअली। तो वो n बाई 2 डिजिट नंबर्स को जो हम ले रहे हैं यहाँ पे 4n बाई 2 डिजिट नंबर्स हो रहे हैं। तो 4n बाई 2 डिजिट नंबर्स जो है हमारा यहाँ पे मल्टीप्लिकेशन ए सी बी डी ए डी और बी सी, इन पे हम सेम वे पे मल्टीप्लिकेशन कर सकते हैं जो प्रोसेस हमने n डिजिट्स पे लगाए हैं। तो मतलब कि उनको फर्दर ब्रेक, n बाई 2 को फर्दर ब्रेक करके n बाई 4 डिजिट्स नंबर पे देखना है। तो मतलब अगर हमारा रिकरेंस जो जो हम प्रोसेस n के n डिजिट नंबर्स के लिए कॉल कर रहे हैं वही सेम प्रोसेस हम n बाई 2 के लिए भी कॉल करेंगे। तो यहाँ पे 4 है तो 4t n बाई 2 इसीलिए, ठीक है। और ईच प्रॉब्लम इज ऑफ साइज n बाई 2 तो इसीलिए n बाई 2। log 4 base 2 is 2 so n square, that's so it's order n square time, yes। so if you since you know master method, मुझे पता भी है तुम लोग मास्टर मेथड पता है, तो this running time is order n square, okay, which is not an improvement of whatever we have done. Since we have already seen that our old algorithm is uh, performing order n square, so yes, so there is no point of doing all this division and all, okay. But there is a catch, so that's why we are not computing AD and BC in this case. You can see that in this algorithm we are just computing 3 multiplications. It's A plus B and C plus D, okay. And from there actually we compute this AD and BC. How? Okay, so look at this A plus B into C plus D. How this is helping us to reduce the running time. This step is actually the catch. Okay. So if you break it, you get this number, right? Now, all we need to find is AC plus BD, AD plus BC. So this is our AD and this is our BC. So can we think of these as AD plus BC equal to A plus B, C plus D minus AC minus BD. Okay. नहीं, तक नहीं कह सकते, अभी के लिए ये पता है, पर यहाँ इसका लोअर बाउंड कुछ प्रूफ नहीं हुआ है कि ये यहाँ तक ही हो सकता है. You can try to find or linear time algorithm or sublinear if you if you can. It's open problem. ये खुला हुआ है, मतलब ओपन है, कोई भी कर सकता है ट्राई. अगर तुम कर सकते हो तो बहुत बढ़िया है इसको linear time में. Okay. तो where was I? Yeah. So now you can see that we compute this AD and BC and their addition by just multiplying these two numbers. And so we just need to compute three multiplications: AD, AC, BD, and A plus B, C plus D. Okay. So now I think the reason that we are doing these steps are clear. Why we are doing all these steps? Is it clear now? और यहाँ पे or is there any doubt? यहाँ पे किसी का doubt है तो बताओ. Okay, we are computing AC. Why we are computing AC and BD? It's clear. Why we are computing A plus B and C plus D? Now it's clear, I think, why we are computing A plus B and C plus D, because it's giving me AD plus BC directly, and from there we can after computing A plus B, C plus D directly, we can get the value of AD plus BC from the step 4. That's why we are performing step 4, that we are subtracting A plus B, C plus D minus AC, AC and BD from A plus B, C plus D. And after that, we add all these terms, because in here you can see the addition is according to this law, this part. Addition is happening because of this. That's why we are adding. So, okay. Okay, so let me just do it all over again. Okay, I'll just execute the algorithm step by step for the for two numbers. So we have this. What are the numbers? 5790 equal to 1345 1345. So first we do what? We compute this as A, we compute this as B, compute this as C, compute this as D. So we get, right, xy equal to 10 to the power 4 AC plus 10 square AD plus BC plus BD. Okay, fine. Okay, so okay, so next is 10 to the power. So okay, so now we compute AD plus BC. That is nothing but A plus B into C plus D minus AC minus BD. So we compute that. So we'll focus on these computations. So first AC. So for AC, we need to call again. AC is what? 57 equal to 57 and C equal to 13. So we break these numbers into single digits. So think of it as, directly you can write it. So if you multiply AC, that would be 10. How many digits are there? 10 square. 10 square, it's AC, so 5 into 1. So it's a single digit multiplication plus 10. This is actually we are computing this 5 into 3 AD plus BC. Na? 5 into 3 AD. Sorry. 5 into 3 plus 7 into 1 plus 7 into 3. Now this is a single digit multiplication. This is a single digit multiplication. So we directly get this answer. This is 50. Sorry. 5 in 10 square into 5. We'll write it in this way. Plus this is now computing this one. This is basically for that we are computing this 5 plus 7 into 7 plus 3, that's 12 and 10, so it's 120 minus we computed AC already 5 and we computed BD in here 21. So from here we can compute it's like what 99 594. Is it correct? Yes, as long as it's a factor of n, then it's not a problem. For example, you can deal with n minus 1, but you have to adjust the coefficients accordingly. What I'm saying is that यहाँ पे, I mean, when we are multiplying two different digit numbers, then we have to be careful about these 10 to the power factors, that how we are adding those numbers. Okay, so since you have already seen that why we are coming up with this kind of rule, so whatever, let's say you have n or m digit numbers, okay, odd लेके बोल रहे थे, okay, okay, अभी तो start कर दिया ये. So can you see that I'm breaking? I'm not going to exercise all these things up. I'm just giving you the example that, okay, I'm computing this one. Now I compute AC from here. Similarly, I'll compute BD and I'll compute A plus B into C plus D. Okay. And now the questions that someone is asking about odd and someone is asking that if the two digit numbers are different. So let's say your X is some n digit numbers. Okay. And when you divide it n by 2, you obtain something like this. And your Y is some m digit numbers. And when you divide it into part by 2, it comes like this. Okay, so if you multiply these two numbers, what are the numbers that you obtain? So if you think about you think about a 3-digit number and a 2-digit number, let's say if your X is of 3-digit number, multiplication is too big. Okay, so if you look at XY, that would be something like n by 2 n plus m by 2 n plus m by 2 AC plus 10 to the power n by 2 AD plus 10 to the power m by 2 BC plus PD. Okay, so now you can see directly computing AC or BD is not the solution. I mean, if BD still works, AC will still work because you can compute n plus m by 2, but it would be difficult to compute AD and BC. Okay, because AD and BC are not sharing the same coefficients like previously. So even if we take it there will be some n minus m by 2 type of factor left with the AD part. So you have to keep it, then keep in mind that one. that you have some factors in there, and your addition, that this part that we have done now in this part 5, this would be a little bit different. Okay, you have to adjust accordingly, but the idea is same. Okay, so you can compute AC, you can compute BD. Okay, and this AC and BD both are n by 2. A is a n by 2 digit number, C is a m by 2 digit number. Similarly, like D is a n by 2 digit number, m by 2 digit number, B is a n by 2 digit number. So your problem will reduce to like multiplying n plus m, n by 2 digit and m by 2 digit numbers. Okay, so you can apply that same process, but you have to be careful about adding these two terms because they are not sharing the same coefficient now. So the same rule that we have applied, a plus b into c plus d equal to uh, we compute that one and then we use that to find AD and BC. That will not work directly. Okay. Okay, clear? That will not work directly. So you have to adjust your coefficients. You can design that rule, but you have to adjust. Okay. Okay. And for odd numbers also, you can just apply the same process. One part is if you maintain like I'll take the first part as 3. If you take not 3, I mean what I'm saying is that if you think about these two as odd numbers but same length, n is odd. Okay, so for odd you can just fix it. Let's say this one is our n by 2 floor. So you also maintain this one is our n by 2 floor. Then you don't have any problem with that because then you know the value of n and you can just execute it. Then everything will be same. Okay. For the one who was asking about odd, odd को हम ऐसे break कर सकते हैं. Okay. Fine. ठीक है. तो for example, if you think about x equal to 5701, y equal to 13456, 570 अच्छा 901 अच्छा okay 57901 and this, then you can think about these as A, these as C, this as B, this as D. Okay. ये so XY would be like compute AC, BC, BD, and A plus B, C plus D. ये अभी क्लियर है ऑड के लिए कैसे करना है? ये ऑड नंबर है 5 डिजिट, तो ऐसे ब्रेक करके ठीक है. सेम पार्ट को मैंने मतलब जो ए का लेंथ लोगे वो भी सी का ही लेंथ लोगे. ठीक है, वैसे कर लोगे तो हो जाएगा. Okay, so how this is improving our running time? So what is the recurrence in this case? How many multiplications we are doing? If you check in this improvement that we are not computing AD and BC, instead we are doing A plus B, C plus D. So we are doing one less multiplication, right? Instead of AD and BC, 3 multiplications. Yes. So the recurrence should be 3 n by 2 plus order n, right? Now if we apply master method or any method you know, even if the basic one, so this is a very simple reconciliation, you will get that this is something like n to the power log 3 base 2. Okay. Which is like something n to the power 1.5, if I'm not wrong, type value. So let me 1.5. So this is a little bit of improvement than our order n square running time. Okay, but in practical, this algorithm is like it's good, but like this is good for long integers also. Like for smaller integers, for small digit numbers, we don't care. But if n is too large, then this kind of techniques will help. Actually, this kind of technique helps to solve the problem. Okay, so the main idea is to like give you an insight about how you can think your usual problems differently. You can view your problems differently. You can apply the techniques that you have learned to you or to your already known problems, and you can see that it can significantly change the computation complexity of these problems. Okay, so okay, this is the problem. Okay, so sir told me to solve another problem in this class, another application. So I'm continuing the tutorial for a little bit longer today, and maybe I will also, actually I have to discuss a little bit more about C programming because when we are trying to do this coding for this algorithm, integer multiplication algorithm, then we have to know a little bit more about C programming. So I will discuss a little bit of pointer and the string that we need for in this case actually to code this problem actually. So the next problem that we discuss, so it's clear, right? Is there any question? So this is the running time of Karatsu algorithm. So if there any question, ask me now, then I'm going to the next problem, which is matrix multiplication problem. Okay, so I guess there is no question. So next problem is matrix multiplication. So all of us are familiar with matrix multiplication. The algorithm that I'm going to discuss is actually I will discuss on n cross n matrix. I will I'll take like matrix multiplication. You know the solid like problem. So given two matrices x and y, if we multiply them, then I want to get the output set, which is the multiplication of these two matrices. Okay, but as you know that matrix multiplication is possible only if the column and the yes, we are discussing the square matrix. Actually, we will discuss the square matrix only. But you can extend this same idea to like non-square matrices also with a little bit of modification. Not much, but it's easy to understand through square matrices. So the main idea is to like understanding the application of divide and conquer. So that's why for simplicity, I am considering this n cross n matrices or square matrices. But I can also apply this techniques into the non-square matrices also, rectangular matrices. If you remember that for true multiplication of two matrices, the column number of the second one should be equal to the row number of the second one, right? Yes, first and second, not one another. I mean, not equal. Yes. So since we are dealing with square matrices, so nothing like this situation will come. So we are dealing with these n cross n matrices. Okay. And there is no restriction to the input of these matrices. So these inputs can be integers, can be rationals, can be anything, any numbers system you want, or any field you want. It's free to use. So you can think of any numbers in there. So what are the elements of Z? So if let's say we denote an element of X to be like Xij is an element of X, and Yij is an element of Y. So what is Zij? Zij should be, it's a multiplication. So ith row and jth column. That means it's a multiplication of ith row of X and jth column of Y, right? So we can say this is the ith row of X multiplied by jth row of jth column of Y. Sorry. Okay, so this basically mathematically you can write it as 1 cross 1. You can formally you can define it. For example, it's k equal to 1 to n x I k y k j. Okay. So what is the size of input in here in this problem? What is the input size? How many inputs are here? We are dealing with a square matrix. Okay, and 1 to n. No. I mean, how many entries are there in a matrix of n cross n size? If you take a n cross n matrix, how many entries are there? There are n rows and n columns. So n into n square entries are there, right? And you are giving input as 2 n cross n matrices. That means your input size is order n square. So your input size equal to order n square. Okay. Now, if you want to compute this matrix multiplication, okay, so basically we are trying to compute this Z matrix. So each entry of this matrix can be computed in, like what is the time that we take to compute an entry Zij? It's a multiplication of n rows and n columns, right? So we are basically doing n multiplication of integers and add them. It's a basically multiplication of n integers and adding them. So this step takes order n time. Okay, and there are order. There are how many elements are there? Order n square. Input size is order n square because you have n square in elements there. Okay. So the question is, what is the question? Kya hai? I mean, the question is, what is the running time of our known algorithm? That how we find the matrix multiplication? We just multiply a row with column corresponding to each position, and we find the value corresponding to each position of the matrix Z, right? That's how we usually computed our matrix multiplication back in school days. So what is the complexity of that algorithm? So we are discussing that one. Okay. We are discussing the running time of, no, it's not order n square. Uh, at one step, so you have this matrix X, and then you have, let me write it. This is your matrix X, this is your matrix Y, and this is your matrix Z. So at one step, you have this ith row, and you have this jth column that determines some ij element of Z. Right? Now, how many elements are there? X is a n cross n matrix, Y is a n cross n matrix. So there are n entries in here. There are n entries in here too. So how when we are multiplying, when we are computing this one, Zij, you can see Zij. What we are computing? We are computing these multiplications basically. So how many xik are there? 1 to n. Okay. Then how many kj are there? 1 to n. And we are multiplying one integer in here to another integer or whatever entry in here to another entry in here. So we know that we can access one element of a matrix in constant time. So how many multiplications we are doing while determining one element Zij? Order n multiplications we are doing, right? And how many Zijs are will be there? It's a n cross n matrix. It's a multiplication of n cross n matrices. So Z must be a n cross n matrix. That means Z has order n square entries, right? So how many times I have to compute this Zij? Order n square many times. And each computation of Zij takes order n time. So that means order n cube. So, okay, let me write. Computing each Zij takes order n time. Number of elements in Z is order n square. Therefore, arithmetic operator has time complexity order n. What do you want to say or what do you want to mean by that? Arithmetic operator has time. Yes, they are that's order in that's order one time actually, not order n. We are assuming that we can multiply and add constant time. Multiply two numbers in constant time. Multiply add two numbers in constant time. That's what we can assume. Okay. So what I'm saying is that you're multiplying these two numbers, this number and this number. This multiplication takes constant time, but how many multiplications are happening in here? Order n multiplications, because there are n elements in here. Number of rows, number of elements in a row is n in X. and number of column elements in Y is n. So there are n multiplications happening in here. So that's why while we are determining Zij, it takes order n time, and there are number of elements in Z is order n square because it's a n cross n matrix. Okay, so total running time order n cube. Okay. Okay, fine. So our known algorithm performs order n cube order n cube like executes the matrix multiplication in order n cube time for square matrices. For yes, it is not good. Can we? The next question is obvious. Can we improve this running time complexity? No, it's not always okay. Okay, maybe later we'll discuss it. Not now. Okay, so now the question is, can we improve this? So again, we are dealing with this divide and conquer algorithm. So we will apply the divide and conquer technique in here. So can you like come up with how we can divide this? Basically, we have already done one algorithm in just now we have done one application of this divide and conquer. So can you think of a similar type division in this case that we can break this problem into smaller sub problems and find the solution for it? So better algorithm. For that, we again use the strategy. Strategies divide and conquer. Yes, Strasson's algorithm is yes. You know Strasson's algorithm. Oh, okay. So apart from Strasson's algorithm, there is this deep Strasson's algorithm is actually a divide and conquer algorithm, but simply divide and conquer could also work. Strasson's algorithm is a little bit of improvement, but it's not good in practical because implementation is quite difficult, and it contains a lot of space. Actually, consume a lot of space. That's why we don't generally use Strasson's algorithm in practical. Now let's say divide and conquer, right? Let's get into the idea. So we want to divide and conquer means that we have a problem. Now we want to like find the sub problems corresponding to this one. So if you think about a matrix x, y, it's a matrix. So it's a square matrix, right? So I want to divide it. Can I divide it by half like this? Like this? Does it work? If we divide it by half like this is no longer a square matrix. So the recursion will not work in this case. Okay. So if we divide by half from the middle also in this way, then each of these is a square matrix. Okay. Each of these is a square matrix. And what is the size of each of these matrices? That would be n by 2 cross n by 2. Okay. So this means that these are perfect for me to apply my recursion. Okay. This is a good sub problem for me because I have reduced our n matrix, n cross n matrix to some n by 2 cross n by 2 matrices, smaller matrices. Okay. So this is the idea. It's similar, almost like most similar to this Katsub algorithm. We will divide this into these smaller matrices A, B, C, D. Call it EFGH. Okay. So where each A, B, C, D and E, F, G, H is a n by 2 cross n by 2 matrix. Okay. So now if you do the matrix multiplication, what do you have? You're basically doing A plus BG, AF plus BH, CE plus DG, CF plus DH. Okay. Okay. Is it okay? Or is there confusion? Like you can take of like you can think of 4 cross 4, a 4 cross 4 matrix, and then you can divide it into 2 cross 2 smaller matrices, and you can check this result. Okay, this will hold. So how many computations are how many computations we are doing in this case? So obviously this will give you the result. So if we can compute this multiplication, this multiplication, these multiplications, all these multiplications, then we are done. Okay. Okay. So we'll be done when we know this multiplication. So how many multiplications we are doing in this case? There are 8, right? Yes, 8. So recursively, when we compute the running time, it would be 8 of Tn by 2. Okay. And how many additions we are doing? No, I mean, okay. See, these 4 additions is not primitive additions. These are matrix additions. That 4 is saying these are matrix additions. This is not primitive additions. That one you are seeing right now. So what we are computing is actually we compute this addition for every position. Okay, so there are order n square additions actually we are performing because there are order n square elements in there. Okay, so it additionally will compute like order n square many additions. Okay. Okay. So these additions are basically matrix additions, and at each step, okay, your subproblem will compute all these. Like each problem will have we actually have n by 2 number of entries in there, and it will also yeah. So each of these have to perform. There are order n square many elements in there, and for each of these elements you are performing this addition, so there would be order n square many additions. Okay, so this is the running time for this is the reconciliation. If you solve this reconciliation, it's order n cube. Okay, which is not an improvement. So this algorithm still does not help us. Okay, so from Karatsuba, I think you have got an idea that if we can somehow reduce the number of multiplications, number of subproblems, then we'll be able to make it faster. So the same idea, same type of idea is applied in Strasson's algorithm. So Strasson's algorithm is basically reduce this 8 to 7. Okay, one less computation. Okay, so how he come up with this idea, that's not clear and that's not known. But he somehow manages to do something like this. I will do an example with 2 cross 2 matrices. But this is what he did. The idea that he has this matrix D, Y, and all these are matrices. Okay, the X is a n cross n matrix. A, B, C, D all are your n by 2 matrices. Y is E, F, G, H. So now you compute these matrices. Okay, P6 is B minus D, E plus H, P7 is A minus C, E plus F. Okay, so we have this matrices. Now we claim that basically that if we multiply this xy, then what we get A plus PG, A plus PD, CE plus DG EF plus DH. So yeah, how it's not known. He somehow came up with this one that if you okay, let me write completely. P5 plus P4 minus P2 plus P6 he somehow came up with this idea that this is equal. It's quite strange. There is no proof, but I can prove that if you do this, then you will get this. And that's a simple computation. Like if you do what is P5, A plus T, E plus H. And P5 and P6. P5, P4. Let me write it. It's long. So if you compute this P4 minus P2 plus P6, then it's AE plus DE plus DH plus AH plus DG minus D, sorry, minus H minus PH plus PG minus TG plus PH minus. So you can see DH cancels, PH cancels out, DD cancels out, DG cancels out, AH cancels out, and that leaves you AE. Yeah, so it's quite strange. If you execute all these given formulas in here, then you will get that this is corresponding to this one, this is corresponding to this one, this is corresponding to this one, but there is no proof that how he obtained this this P1, P2, P3, P4s. Nobody knows. So he came up with these 7 matrices, and as you can see that since it's corresponding to these matrices, that means that we can simply compute this smaller matrices to obtain the total computation of x and y, and multiplication of x and y. So in this case, the running time will be the addition and subtraction that will take the same time. So that will be Tn by 2 plus order n square. So if you check, this is something like you can apply master method also. So in this case, it will be approximately order, I think, n to the power 2 point something, 2.8 or something. Yeah, about 2.8. Basically, this is nothing but order n to the power log 7 base 2. Okay. So this is the improvement that we get from from n cube to 2.8. So it's not a very significant difference, and this algorithm is actually quite requires a lot of space, because you can see that we have done 7 multiplications, we have to do 7 recurrences, also you have to store these values, so it takes a lot of space additionally. Our like initial algorithm of matrix multiplication, that if you can simply is still significant in complexity area, because if it doesn't seem much, but reducing complexity by 0.1 even is very difficult. Okay, so it's so it's important, it's very important, and it's quite it's although it's like, if you want to apply this is a very like, it's not good in implementation, but theoretically it's a very good improvement over the known algorithm. The known algorithm is actually easy to implement rather than this one. Okay, but that does not require any additional spaces. This requires additional spaces. All of this, like divide and conquer, requires not all of this. I mean, this matrix multiplication algorithm that we have seen. We have seen 2 algorithms in here. If you can see in matrix multiplication, we have seen one using divide and conquer only, and then Strasson's algorithm, that is a little bit of modification of that one. So yes, Strasson's is the last one. There is another algorithm I have discussed. The first divide and conquer algorithm, the running time is tn equal to tn by 2. This idea was there. Strassons actually gave this strange polynomial, this strange matrices, 7 matrices, that if you multiply, if you obtain these multiplications, then you can obtain the whole multiplication of x and y. So this is order. So the first algorithm, order n cube, that also requires some additional spaces, as well as Strassen. So implementation wise, it's a bit not good to implement, but it's okay. Complexity wise, it's fine. Okay. So this is for today's class. Up to now, we have done these 2 problems. Now, basically, I wanted to write the. Actually, I wanted to solve the problem for Karlsruhe problem. Actually, wanted to uh, write the code for integer multiplications, but for n-digit multiplication, you need to know in C. Actually, you need to know I have heard that I've seen that some of you have difficulties using C, uh, and this implementation of n-digit multiplications. Actually, you have to use a thing called string. I think if you are familiar with strings, then it's fine. If it is not, I actually discussed about strings right now, and also we need pointers. Okay, without this, it will be very difficult to implement this coding of multiplications. So I will focus on mainly this basics of C, and if we have time, then we will go for the coding. So let's start. So the first thing I want to discuss about any one of strings in C actually. in this part. Strings in C. So how many of you are aware of this thing called strings? You don't know about strings? I mean, I think some. Yes, the same thing, It's so in C, it's actually yes. In same thing in here also, it's written inside this. So basically, string is basically an array of characters, and it's actually terminated by some this /0. This is called null character. It's terminated by this. Okay, so this null character is very important. This actually denotes that the string is ending in here, and it's actually very important to manipulate the strings when we. Uh, so, for example, we can see difficult switch between. So let's say so there is no actually data type in C. String as a data type, it's not present in C. So mark it like there is no data type called string in C. So in C, you will not find this as a data type. You have to use characters for that. Okay. Now, how do you define strings? So char is corresponding to the character variable. Uh, I think if I can shift, is it okay if I shift to the GDB? Because although I have to write something. Okay, I will just. I'll just. Can I? Okay, the character of, let's say, so when we are defining string, let's say character str, and we define some uh, array type. This is an array of characters, and the second bracket you wrote like ABCD. Okay. So this is basically what it means. It means that you have created is that an array of the form A, B, C, D, and it's ending with a null character. So this is created. Okay. So when we write that character str equal to ABCD, so this implying that it actually creates an array having each of these as an element of that array. Okay. So I will just write about how you're reading strings, and then I'll move to the coding area where I will show you how we are reading strings and uh, we are like using that. And okay, before that I will discuss about a little bit about pointers also, because I want to convey both these things today in this class and to show like application of both in this class. Okay. Yeah, okay, I'm trying to write clearly. I don't know. My usual handwriting is very bad. So anyway, we how we are reading this string is basically for like you have seen for integer data types we are using %d. For float it's %f. For strings we use %s. Okay, so remember it's you are defining it as a array of characters. Okay, and if you write %c, that would be corresponding to an element of that array, because then each of the element of that array is a character. Okay, see, whenever you are writing something like this, this is generating an array like this. So if you write like %c instead of %s, this %s actually denoting all this. It will actually represent the whole array, whereas %c will corresponding to an element of that array. If you have to specify the element of that array. Okay, so this is a basic difference, that we are not using %c in here, we are using %s whenever we are trying to use strings. Okay, so how to read a string? Okay, so obviously we have or like taking input. We have seen that we are using scanf function for that. Right? We use scanf function for taking inputs. Okay, so there is a problem with scanf in this case, because scanf will read until there is a space. Like suppose you are typing a lot of typing kind of a line. Let's say I am. If you type I am and there is a space, scanf won't be able to read it. Okay, so in that case, we actually prefer another function. There are several functions, though, but this f gets, or there is another one gets, but f gets is better because it actually doesn't. It actually takes like you can bound the number of maximum number of characters it can read, so it doesn't like overflow. Whereas gets does not have any maximum limit of reading, so it can read a lot. So there is a function fgets. Okay, so fgets is actually, for example, like if you want to give that as something like I am, then you have to define the length of this also. Let's say it's 40. Okay, so what this fgets is, it will read. So okay, the input is not given. You will give the input. This is I define this. Okay, this 40 means the size of the array. Fgets, I'm writing fgets actually. I'm not done with fgets. This fgets basically give you the fgets. The difference between fgets and scanf is that scanf, like if you give an input like I am, whereas space is there, or there is like /n is there, it will read like up to this and then it will stop. It will not read the space. Whereas fgets will read with space and whatever is written in there until a new line command is there. Okay, so it will read up to that. Plus, it will you can give like it will also take the maximum number. You can also give you the maximum number of characters uh, it can count. You can bound it. Okay, so there are three components in fgets basically. One is the string that you want to give input. Another is the maximum number of characters, including the null characters. And there is thing called standard. Actually, it's a input stream, but for us, for our purpose, it's stdin, which is standard input. Okay, so this is basically a pointer to the string where the input is stored. I'll come to the now. I'll come to the thing which is what is called pointer. So this is more or less the settings for fgets. I will describe when I will do the coding. I think then it will be more clear. So next we will come to the pointers. Okay. Let me just I'm coming. Just give me a few 1 minute. Okay. Okay. So next is pointer. Okay. So next is pointer. Pointers in C. So this is a very important thing. So what pointer does is that it actually stores the address of a value. So pointer is itself a variable. Okay, and this variable actually pointer is a variable that stores the address, actually the memory address. So everyone has idea about this memory address of some other variable. So for example, like when you define a variable, let's say you define integer x. Okay. So what you do is that you in the memory is kind of block type. It has a lot of blocks in it. If you know that it kind of looks like a array type. Its figure is something like its memory blocks are there. So these are something like memory blocks. So your when you write this integer x, is basically what computer does is that it allocates some space, let's say this one, for this variable x, and this space has an address. Address means it has a memory address. So what is this place, like in where it's the this x value x is stored. Okay. Yes, pointers actually have the address of that variable. So whenever you define a variable pointer, okay, so pointers are generally defined with a star and a type. Data type is also there, the which type of value. So if you define something, this pointer, let's say this is your pointer, what stores inside this is the address, is a pointer of x, pointer to x actually. So this basically stores the address of this pointer, the address of this variable x. Okay, so pointer is itself a variable. Okay, like a equal to 10, integer star b, and you define, it did not define b equal to, okay, b equal to and a. In b contains the address of in and c. No, this is no, in c, no, not c. I mean b b is actually contains the address of a. No, percentage is actually it's not pointer. It's actually percentage is corresponding to the string. You can say it's like the percent d of integers. B, yes. B actually contains the address of a. Yes, the pointer is the B is a pointer to a, and that means that B is storing the address of a. Okay. Previous pointers too. Okay. See, pointers are variables. Okay. So if you put a pointer to another pointer, that means what? You are pointing to some variable. Your pointer is a variable. Okay. You are pointing to that location, and the value inside that pointer, that where you are pointing at, that is actually pointing inside, pointing an address, actually storing an address, actually stored an address of the variable that is it was pointing to. So for example, if you are talking about that pointer of x type thing, okay, that you are saying that some pointers indicate the previous pointers. Its previous pointers is something like this, that you can do this, but there is no like previous pointer. Previous means that I mean there will be some order in there. So I don't know what you mean by ordering, but you can do like this thing. You can do that. You can define a pointer of some variable, and you can define another pointer that is pointing towards that pointer of x. You can do that. But it's basically pointing towards the location where the address of that is stored. X is stored. Okay, so so I think the idea is clear. The what is pointer and what is stored inside the pointer. Okay, so pointer is basically this address, and when you call this pointer using, yes, linked list has this kind of, but not previous. It's actually where does it pointing? If you think about linked list are like that. It has a pointer to its previous node. It's not pointer towards a pointer. It has a pointer towards its previous node, and also a node. It also contains a pointer from its uh, next node also. Okay, same ideas like when you have if you studied the trees, I don't know whether you have studied or not. If you study binary search tree or something like that, then there are pointers actually. So from parent to child, there are pointers like this. From parent to child and child, this one. Okay, so there are pointers like that. So I think then you have the idea of pointers, right? So okay, fine. Then it's easy for me. Then I can skip. Then I can skip the pointers, I think. Then I don't need to explain it. In C, okay, let me just give some syntaxes, and that and I'll end it in there, and then I'll move to the coding. So how we declare the pointer is that we have data type star name of the pointer. Okay. Who has the address of very last pointer? In where? Address of last pointer. I don't know what is last. In linked list? In linked list, if you think about the last node, it just have the pointer towards the previous node, and the list is ending there. There is null. If you if you give another, if you add another node, you can add it like at the end. Then you can give a pointer towards that node, and you can also like add. I think in linked list you can add in middle also. You just have to adjust the pointers of the two nodes in between where you are adding the node. Okay, so it's not about that. It's just what pointers are implying and what do you like when you're calling them, what are they giving us? Okay, so this is the way we declare a pointer. For example, like integer star t. This way we can define, or like we can also initialize it. Like we can give a value. Uh, now it corresponds to some variable x, because pointers are defined when there are some variables. Actually, because it's pointing to some variable. So if you write just integer star p, what does it mean? If you don't assign anything to it, it means that it's a pointer, but it doesn't know where to point, because the variable is not given in there. So that's why you have to like define a variable for which you are defining a pointer. Okay, you have to have a variable for which you are defining a pointer, and mind it, this data type should be corresponding to the value it's pointing to. Okay, so this x is an integer type. That's why I am defining integer star p. If it is a character type, I can define character star p. Okay, so this is the thing, like you have to keep in mind that what is the variable that it's pointing to, and your data type should be same as the variable that the pointer is pointing to. Okay, you have to keep it in mind while defining the while initializing and also defining the pointers, declaring the pointers, or declaring, that's the correct term. So dereferencing, you have idea about dereference? Then I'm not going to discuss dereferencing a pointer, or dereference. You can see the handwriting is not clear. So do you have any idea about dereference of a pointer? Dereference a pointer? How to dereference? So dereference means that I am now asking that what is the value? Yes, it's in C++ actually, the one you are writing, or Python. I think it's C++ that you are referring to. That's basically is accessing the value where it's pointing to. So for example, if it is like, if you're let's say you define n equal to 10 and integer pointer equal to address of n, so you give it. So if you ask that the star ptr, this is basically the value stored at the location is pointing to. So if this is your n, the variable n, and this is its address to define the pointer. So the value stored in here is this address, but when you call star ptr, it's basically pointing to the value inside this, that is 10. Okay, so this is called dereferencing, that you are accessing the value. Previously, like we have seen that pointer is the value inside the pointer variable. That pointer variable stores the value of the address to the variable it's pointing to. Now we can see that we can access to that value, and not only that, we can also modify or manipulate that value also using this dereferencing. Okay, we can also modify that value, we can change that value, we can do things with that. Okay, using dereferencing. So this is a very important technique that we use. Actually, we are going to use for both these problems, matrix multiplication and Karlsruhe. I mean, Karlsruhe is just integer multiplication. So like n-digit multiplication, and both we need these things. But first, I will give you some idea about like how these codings are. I mean, like how you are dealing with strings. We have read it now. See it in the coding part. Okay, so closing it. Fine. I think my screen is visible, right? One and address we use yes. Yes, percent %p is corresponding to the address. Uh, that actually, if you want to print the address. Oh, there is one more thing I forgot. There is another header file actually that in string that helps us to. Okay, so we will see. So there is. Okay, let me just first a simple thing. So we were talking about strings, right? So the way we are defining is right A B C D. Few. So code will give you ABCD. Okay, so the idea, like why we are focusing on character, I mean strings, is that because we will convert our numbers into strings, and from there we will do the computations, and after that we will convert them back to the numbers. Okay, so that's the idea behind this long integer multiplication, or like integer multiplication algorithm. Sorry, sorry, executing this integer multiplication. Uh, so this is the string that we are talking about, and I think I have covered how to take an input, right? So for that, you have to remove it. Say, give it size around, let's say 40. So scanf. So let's say I'm using scanf. Okay. So for scanf, we can do the same thing. %s. Now, let me try to give a space in the space or tab in there. Okay. So you can see that after space it doesn't count. That's what I was saying. That it will not consider if there is a space or special character is there. Space or tab or a new line is in there. Okay. So for that we are using these things called fkits. Now for fkits you need the following things. This str, this is actually the name, although actually it's the pointer to the variable where we are storing our string. Okay, so whatever we are entering, it will be this is uh, telling the function that whatever the input will be, it will be stored inside this str. Okay, and maximum character length. So let's say I bound it with 330, and standard input output, which is denoted by stdio. Now let's say now we run code and have ABCD. We just see it's coming like this. Okay. Okay, fine. So these are the difference. Okay. So that's why we are using gates and fgates. Sorry, there is also gates, but fgates is better. Just mention the length of the string, maximum length you wanted to, and it will give you. Okay. And now the thing that I wanted to use. It's a header. It's header file. string.h. So what this string.h does is it contains some functions, some 30 is the maximum character length that FKets can read, and stdin stands for standard input output. I mean the like from where it's taking the input, standard input. Sorry. So these are like input. You can think of like the platform we are using is standard input output. So this stdin is corresponding to the standard input, but it can be like anything. You can change it. Okay, it is changeable, but for now, just think that stdin is for standard input. This is work like user input. Yes, your see if you this if you are asking about fgets function, your user input is it's actually depending on like no, I mean user input. I don't know what you mean by user input. It's basically the what is like standard input. So there are like numerous ways you can take the inputs in there. There are stdio dot in. I mean, this is the way we are dealing with this, but there are yes, that's what I'm saying. That you can define it according in your way, whatever. I don't know. There are some different methods also to define to take inputs and outputs. But for that, and this stdin stands for whatever we are dealing with. I mean, whatever we usually do in here. There are some others. There may be some others. Screen not visible. All right. So I was talking about this string.h function. It is helpful to determine the length of the string, and it contains some function actually, not determine the length of the what I'm saying. This actually contains a function called star length, and star copy. There are a lot of functions actually inside corresponding to the string length and string copy, string concatenation. You can do all of these using single functions. So this is very useful. So let me write this one. So the function I'm talking about is first what I will use is string length. Okay. So since it's a length, so it's an integer. So this star length outputs an integer. Okay. This is the function star length. So in argument, you just have to pass the string. For our case, it's str. Okay. do. Okay. Oh, long unsigned. Okay. 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 Unsigned integer. Okay. Put for it. Directly give the input. Enter the string. Yeah. So it's coming. Okay. Maybe LD. It's talking about LD. Okay. Fine. Okay. So talking about anything. So now it works. Yeah. So the error was because we were using integers, but the star length function having an unsigned integer in it as well as long integers. So %LD. And the type was different. Okay, fine. Now let's. So this string dot h that we need to use because we will be using this string length function. There are some more functions also, but I'm not going to discuss them. And now we need another thing, which is called pointer. So, and I'll just show some applications because I think I don't have much time. And I expect that you guys will try to write the code or so any integer variable x. I'll just give you this example and then let us know if so you want to call this tr, what do you get? Sorry, there is connection problem. I don't know, something happened with the network. It's not showing. Oh, wait, what is it? Actually, I'm sorry, there was an internet issue as well as I got a call. So anyway, what I was trying to do the almost time. What I was trying to do is writing code for the pointers, but okay, just let me write. I got the net back. So again this. So it's again the address is storing negative value. It's actually because of the address. Anyway, it's coming. This is the address that storing this value 10. Okay, and similarly, like you can also do this. Yeah. Oh, okay. So I forgot to give that new line. Here you can see. Yeah, the value is coming in here. So that's what someone is saying, that the value coming at this point. So this is what I actually wanted to do is to convert these strings to convert numbers to strings, and then computing the multiplication, and then convert them into strings, and then from there to number again. So maybe I will do that in the next class and see this multiplication problem in the next class. Okay, thank you everyone. Uh, there is no code to paste, so I'm skipping this one. I will upload the tutorial sheet. Yeah, so okay, was my screen visible throughout the time, or it's just I cannot see? I think it was not for the last 2-3 minutes. Yeah. That's what I thought. Okay, fine. Okay, fine. There is no code actually was there. I was just writing the pointers and their implementations. I have actually discussed, so you can try this on your own and try to find the pointers. I mean, try to write the codes. So that's it. We'll do the coding for these two problems in the next class. Next class, we will focus on the coding. Okay, thank you everyone.